Hello and welcome to this video on how high do my correlations need to be in order to conduct a factor analysis. My name is Geiser. I'm an instructor and statistical consultant with QuantFish. On this channel I present weekly statistics tutorials. On Tuesdays I usually address an issue in the Mplus software. On Thursdays I address more general topics in multivariate statistics. If this is something that interests you, then please subscribe to this channel. Also, don't forget to hit the like button, to check out the description for additional resources, and to leave a comment in the comment section if you like. In this video, I want to address a frequently asked question about factor analysis. And so that question is about whether you need to have a certain certain size of correlations in your data in order to perform a factor analysis. So in other words, is there a specific cutoff value that you should look for? For example, should all the correlations be 0.3 or greater? Is there a benchmark, a cutoff value below which you shouldn't do a factor analysis? And so that's a question that people sometimes have, is my correlation matrix, so say, good enough in order to perform a factor analysis? And so that's a legitimate question because obviously factor analysis, both exploratory factor analysis and confirmatory factor analysis, are about explaining or accounting for correlations among observed variables. So if the observed variables don't correlate or don't correlate beyond chance correlations, then you would not end up with any meaningful factors or latent variables in either an exploratory factor analysis or a confirmatory factor analysis. So definitely having correlations is a prerequisite for a factor analysis. Having all zero correlations would not be useful or would not be appropriate for running a factor analysis. That's a very minimal criterion. So say you have to have some correlations, and those shouldn't all be chance correlations. So meaning they should be different from zero. Now, not all of them need to be different from zero, but you should have at least some correlations that are not zero in the population. And so one way in which you can test that very basic criterion of having, so say, some correlations that are above chance level in terms of their magnitude is to fit a so-called baseline model or independence model. And so some programs for structural equation modeling, such as, for example, Mplus, will do that for you automatically when you run any kind of confirmatory factor analysis model or structural equation model. They will give you not only a chi-square test of model fit for the model that you specified, but also they'll give you an independence or baseline model chi-square. And then you can take a look at whether that baseline model chi-square is significant. The baseline model assumes that the covariances in the observed variables, or among the observed variables, I should say, are all zero. So that's to say the implication of that model, that your covariance matrix among observed variables in the population is a diagonal matrix where you only have variances but no covariances in the population. And so that model that assumes zero covariances or zero correlations among observed variables is tested against your observed sample covariance matrix, and then a chi-square test is performed, and the chi-square test is about testing the null hypothesis that the independence model fits the data in the population. And so if the chi-square value is significant, then it means that model is rejected. And that should be the case typically, so that you should have at least some correlations in your data that are not zero. Otherwise, you would almost have to assume that there's some kind of data error. But so that's to say one way in which you can test that and can check whether you have above chance level correlations in terms of their magnitude, fitting this independence model, looking at the chi-square test. If the chi-square test is significant, it means there are some substantial correlations if the baseline model is not rejected, meaning if you get a large p-value for your chi-square test for the baseline model, then you would have to think. Then first of all, I would think of a data error or a software problem where maybe your data isn't processed correctly and check for that. Otherwise, this would indicate that there really aren't any substantial correlations in your data and that a factor analysis really wouldn't make sense. So that would be one thing to look at, and maybe not a bad thing to check anyway, to make sure that your correlations actually are meaningful. Of course, you should also take a look at your correlation matrix, and you should check whether the observed correlations are in line with your theoretical expectations, both in terms of their magnitude and in terms of their sign, meaning positive correlations where you expect positive associations between variables, negative where you expect negative relationships, and so on. So you should always check your data and check your observed correlations. Now, the other question is there some sort of benchmark to say, oh, it's not worth doing a factor analysis when your correlations are below 0.3 or when many are below 0.3? And there I would say this is kind of an arbitrary criterion that I don't agree with, something like that, because it doesn't make sense to me. In a factor analysis, there could be factors that are unrelated or nearly unrelated, and then you wouldn't expect to see strong correlations between all variables or any correlations. So there could be groups of variables that are highly correlated among themselves because within that group of variables, those variables all measure the same factor, but then maybe that group of variables is not so highly or not at all correlated with another group of variables because those factors are independent or are not related to one another, and then that would be something that wouldn't be unexpected or wouldn't be problematic to have certain correlations that are near zero or exactly zero in your correlation matrix. Now, what would it indicate if you had generally low correlations in your data? That could mean that there's a lot of measurement errors. So that would be one explanation, that the reliabilities of the variables are rather small, causing a lot of random noise that waters down, or we say attenuates, the correlation. So having, for example, lots of item level data where you look at the correlations between single items, maybe those single items aren't so reliable, and then as a result the correlations among them aren't so high, which is not necessarily a problem, because one of the very goals of factor analysis is to account for measurement error and separate measurement error from the common factor or true score variance in the model. And so this is then not necessarily the problem as long as the reliabilities are plausible, the correlations are plausible. So there could be cases where you have relatively small correlations. And of course, always think of some data error. Always make sure you don't have artifacts in your data, maybe outliers, extreme values, something like that. This is always something that we should check first before we run a factor analysis or other kind of sophisticated analysis. And by the way, all those points that I mentioned here in this video apply not only to factor analysis, but also to path analysis and general structural equation modeling, where we would have the same issues, where correlations need not be high. If correlations are small, then we should think about why that is the case. Is it maybe due to small reliabilities of the indicators, or are there other reasons that cause those correlations to be relatively small? Maybe method effects, rater effects, something like that. Now, when you have strong correlations, then obviously that is often a good thing. That could indicate that your measures are highly reliable, strongly related, but it's also not always good, because sometimes very high correlations among variables can indicate a lack of discriminant validity, meaning that all the measures really may indicate the same thing, and that's maybe not what you wanted. So for discriminant validity, we want certain constructs, certain factors to not be too highly correlated, and so then that's also an aspect to consider. So really strong correlations are sometimes good, but not always exactly what you want. So always make sure that what you have is plausible. Don't rely on complicated statistical analysis alone, and trust them above and beyond, so say looking at your simple data. So always make sure your simple statistics make sense. Mean, standard deviations, correlations, these sorts of things, plots, look at distributions of the data, look at scatter plots, and make sure everything is plausible and makes sense before you run a sophisticated analysis such as a factor analysis or a structural equation model. I hope you found this video useful as you get started with factor analysis or structural equation modeling. If you did, then please don't forget to hit the like button and to subscribe to this channel. Check out the description for additional resources. Leave a comment in the comment section if you like, and I'll see you again next week.